In the previous two videos, we just learned how recurrent neural network uses a chain-like structures to make use of its existing predictions for improving future predictions. And then we dived into its mathematical representations to see how these concepts can be achieved. Now we have a better understanding about the recurrent neural network, and it's time for us to build a recurrent neural network with the use of TensorFlow Keras. Let's go ahead and get started. TensorFlow Keras provides a recurrent neural network API, and it already built in a few functions, few layers that includes the RNN, LSTM, GRU, and we just need to plug and play. We do not need to build it from scratch. And at the same time, it also allows us to customize our own recurrent neural network layers, just in case if we would like to have that, we can just modify the algorithms inside the RNN layers, and it allows us to quickly prototype different research ideas in a flexible way with minimal changes. And in these examples, we are going to build a recurrent neural network. We're going to build a simple RNN, so we need to import the RNN layers, and also we need to have some dense layers to improve the learning algorithms. And at the same time, what we're going to do is to use the sequential models. And that is pretty much about the layers and the models that we are going to import. And on the other hand, for the data set, what we are going to do is to use the data set that contains 60,000 training and 10,000 test handwritten digits in 10 class. What we are going to do is to classify these handwritten digits in 10 classes. And first thing first, we are going to import the NumPy and also import the TensorFlow, just like what I mentioned. We are going to import the simple RNN and also dense layers, and we're going to use the handwritten digits data set. And I don't think we need this. Let's remove this one. And we're going to import the matplotlibs for some plotting. So let's run this cell. Let's take a look on the data sets that we have. The MNIST database contains the handwritten digits that has the 60,000 examples and also 10,000 examples for testing data and 60,000 examples for training set. The classes are completely mutually exclusive. That means in one picture, in one image, it only contains one classes. And here are the classes. Label 0 represents the 0, 1 represents 1, and so and so. Now let's load the dataset into the training image, training labels, testing image, and also testing label. After we load the models, we would like to normalize the data. The image here are stored in 20x by 20x numpys array with pixel value ranging from 0 to 255. Therefore, we are going to divide the training image, the testing image by 255 to normalize the pixel values to make it between 0 and 1. Now let's run this cell. And the next things that we want to do is to provide them a class names and make it store in a list. So 0 represent the number 0, 1 represent the number 1, and so and so. And let's run this cell. Now let's explore a little bit of the set of the image that we have. Say for example, the shapes of the training and also testing image. Just like what we mentioned before, it contains 60,000 samples, and then each of the image are 20x by 20x pixels. And we also have the training labels, which is a vectors that contains 60,000 valued elements as well. Similarly, we can check out the shapes of the test image and also test label, and we have the 10,000 sample for the testing image, and it also must to be 20x by 20x in pixel, and again it also contains a vectors for its corresponding label. The label value, let's take a look on the label value as well. The label value range from 0 to 9 and then corresponding to these lists of class name. And let's take a look on the pixel value and take a look on the image that we have. The pixel value range from 0 to 1 because we just normalize the pixel value. And this is the numbers, or this is the image that we have. And this is the image 5, and then we have the corresponding label 5, and 0 we have its corresponding label 0s, and so and so. Now we are ready to build a model. This will be a very simple model in this exercise, because the whole point of this exercise is to let you know how you could possibly implement the simple RNN store, the RNN layers. There's two layers that we are going to build or going to add into these sequential models. The first layer is the RNN layers that contains 100 units, because this is the first layers. We also need to provide the input shapes, which is 20x by 20x pixel. And then we are going to add a output layers, because we're going to classify 10 classes. So we will have 10 units as the output with the use of the dense layer. And also because we're going to classify the 10 classes, we are going to use the softmax. Now let's run this out, and this is the complete architecture of this simple model. Just like what I mentioned, the first layer is the RNN layers, and the last layer is a dense layers with 10 units for the 10 output with the use of activations function softmax. And then we are ready to compile the models. We are going to use the atoms as the optimizers, because we've already provided used the softmax activation functions, so we did not need to. We can set the from logic equals to false here, and then we are going to use the sparse, categorical, cost, entropies, because these labels are as an integers. So sparse, categorical, cost, entropies will be used because they are not represented in a one-shot representations. And let's compile these models. And now we are ready to train the models. What we're going to do is to just fit the models and then use an historical objects to store the training process. And also we are going to use the training image, train labels for the training set, and then for the text image and text label for the validation set. And we're going to train it with 10 epoch. Now let's run this model. Once we've trained the models, you should see after 10 epoch, the models which around accuracy it's around 96% on the training data, and around 96% for the testing, for the validations data as well. Now we can pull out the training curve, training history to see how it changed in terms of the accuracy along with each of the epoch. And of course, we can also evaluate the evaluates the model with the testing image and testing labels to see how accurate or how much that we could reach. It turns out that these recurrent neural networks have achieved a text accuracy around 96%. This is not too bad with this simple model. With the training models, we can also use it to make predictions. Let's predict 16 image, and the correct predictions labels are blue, and the incorrect predictions label are in red. The number indicates the percentage indicates the confidence for the predicted labels, because we've used the softmax activation functions at the last layer. Now, if I run this out, here are the results. You can see that most of them are correct, and we got 2 incorrect recognitions. You can see that for these classifications, it classifies it as a 3, but at the end up is a line. And for this one, it classifies as a 6, but it ends up is a 5. So even you can see that even it has a very, very high confidence about its predictions, the model can be wrong sometimes. In this video, we have just gone through a very simple recurrent neural network and learned how to build it with the use of TensorFlow Keras. In the next video, we'll dive deeper in the recurrent neural network to understand the pitfalls about it and how we can solve those critical problems. See you in the next video. Bye-bye.